Assembly line balancing is a subject of active research. The problems considered typically involve a set of tasks that must be allocated among stations. And those tasks, in addition to having some processing time, which is shown here, there's the number above each node, the number inside is just an index of the task, right? The tasks also have dependencies, which we call precedence relationships. What this means is, for example, task 10 requires that task 1 is finished before task 10 is started. And also, when it is finished, we can perform task 11 and task 12, right? And so precedence relationships are not linear, as we had in our example for the Nova Cruz scooter, right? There are some partial dependencies. So we have, for example, with task 11 and task 5, we can do either of them first or second, but task 11 and task 10 are dependent. Task 10 has to be finished before 11. Notice they can be actually done on the same station, but they can also be done on different stations, as long as 10 is on an earlier station than 11, right? So if we were to schedule those tasks, right, one can, for example, try to assign them in a forward manner. And there is a heuristic that was published quite long ago from 1963, which tries to find the best possible set of tasks for each station one at a time, and then builds a solution forward. And then in this example, it actually creates a lot of idle time for the last station, and even the second last has some more idle time, right? Assuming the cycle time for which we design is 16 time units. Now, my own work from 2003, we created a bidirectional heuristic, applying the Hoffman heuristic from 63 bidirectionally in multiple times. And this kind of heuristic can create solutions that are sometimes better in terms of the saving one or more stations. So you see for this example, the solution is actually 3 stations forward, 4 stations backward, and the total stations utilized are now 7 compared to the earlier solution, which was created in one direction that had 8 stations utilized. So of course we can now save because we need one less worker, for example, to produce this. In more recent papers often consider robotic assembly lines. And so this is an example of an assembly line which installs components on printed circuit boards, right? And there are robots, right? So the idea is this is 5 stations. This is symbolizing the robot that is actually installing components on the printed circuit boards. But the interesting thing is that the boards themselves, the products, are wider than the space that is accessible by a robot. And so, for example, in this case, this robot can install parts on this side, the gray part visible by this or accessible by this robot. And this robot could work on the same product on these parts, right? So the problem becomes more interesting because you don't have, like a scooter was, the example of the scooter was always on one station. In this case, products might extend across different stations, and then you have to work in such a way that when you stop the movement of those products, which are on some kind of conveyor belt, you have to stop them at such a time where the robot can install the components and have enough work during each stage, right? So the problems become different, right? The balancing act is still necessary, assembly line balancing and optimization, in order to utilize this well. And also the interesting part is that the boards can be, some products that are produced might be shorter, some might be longer. So the product really changes its nature. It could be that we have boards that extend over more than 3 stations, even 4 or 5 stations at the same time. So the problem becomes interesting. I actually have a work in 2017 that is proposing a mathematical model to optimize this kind of assembly line.